The first example we're going to look at is just finding the displacement in one dimension. So delta x is what we're trying to find. X initial is equal to 7 meters. X final is equal to 2 meters. Now remember what this means on a number line. It means that out here we have x equals 2. Out here we have x equals 7. And that we are starting at x equals 7 and we end up, now this is x initial, and we are ending up over here at x equals 2. Now, our position vector, now this is all dimensional, it's all in a straight line, so there's no two-dimensional aspect to this, but I'm drawing the arrows not on top of each other so we can see what's going on. And the position vector goes from the origin to the location of the vector itself. So this is what x final looks like in terms of position. The vector for x final is that arrow. The vector for x initial is that arrow. Now, what we're looking for is delta x. And delta x goes from where you started to where you ended. That's the displacement by definition. This is delta x, which is equal to d. So to show this, we start with delta x is equal to x final minus x initial. X final is 2 meters. X initial is 7 meters. And that's going to give us minus 5 meters. If we do this with arrows, then what we're doing is this. We're saying we have x final minus x initial, but that's really x final plus a negative x initial. So let's draw out our vectors. We have x final, this is our starting point, so we have x final is this, and then a negative x initial is this length, but it points to the left. So that becomes that. And what we're looking for goes from the origin, or from the tail of the first vector, to the head of the last. So we're still being consistent with what we learned in the prior videos. Alright, so that one was pretty easy peasy. Okay, so let's take a look now at one that's a little more challenging. And this is going to be for a two-dimensional position vector. Now remember that we use the letter R to represent a position in 2 dimensions. And delta R represents the displacement. And it is in 2 dimensions. So for that, what I'm going to do is, let me give you the 2 points. We're going to say that R initial is equal to this coordinate pair, 3, 7 meters. R final is equal to 8, minus 1. Remember that it goes x, y. So the left column is x, the right column is y. So if we plot this out on a graph, this is what we get. We have our first coordinate. Let's do this. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. All right. So our initial position is at 3, 7. So that's 1, 2, 3. all the way up here at 7, and so that is our initial. Our final is at 8 minus 1, so here's 8 and here's minus 1. So the position vector goes from the origin here. It's going to go from the origin to the location of that vector, of that position. And then this position vector goes from the origin to that location. Now, we can pull those out to the side, and if we just draw a quick sketch of our diagram, we know that delta R is equal to R final minus R initial. And so that becomes R final plus a negative R initial. So R initial starts out this long, but the head points on the other, in the other direction. The arrow points the other way. So we're going to have R final, R initial, R final. So we're going to have R final. Here's our starting point. And then it's going to be a negative R initial, so it's this arrow just pointing down in the opposite direction. And our resultant vector goes from the origin to the head of the last vector. So this is delta R. That's what we should see. Now, if you were to take this arrow and drag it up to here, you would see that this becomes delta R. This is delta R. And that makes sense because by definition, displacement is how far you travel in a straight line, and it has a direction. So we went from here to here. So that would be our displacement. That makes a lot of sense. Okay, so in order to finish solving this problem, we need to set up our table. And so what we have here is the x column, the y column, vector R initial, R final, and delta R. These are the things that we're looking for. Now, our initial is 3, 7, but we're not adding our initial, we're subtracting it. Look down here. See, right here, we're adding the negative. So what's the negative of 3? The negative 3 is minus 3. What's the negative of 7? Minus 7. Our final is 8 minus 1. And so delta R is just the sum of this. So 8 minus 3 is 5. Minus 7 plus a minus 1 is a minus 8. Now we need to determine the magnitude or the length of this vector. And so to get the length, we use the Pythagorean theorem. So the magnitude of delta R is equal to the square root of 5 squared plus 8 squared. So delta R, the magnitude of delta R, is equal to 9.4 meters. To get the angle theta, we're going to have the inverse tangent of y over x, so that's going to be 8 over 5. Remember that you want to leave off that negative sign, and when we assign our direction, we know that that's going to be pointing in the down direction. This is the angle that we have found using the inverse tangent function. And so we would say that that's going to be an angle which is below the x-axis. If these were cardinal directions for north, south, east, and west, then we would say that this is going to be a negative 8. So this becomes south of east, which is down and to the right. Now let's finish getting our direction. So let's get our calculator out. And we're going to do the inverse tangent of 8 over 5. And that's 58 degrees. below the x-axis. And more specifically, it's below the positive x-axis.